All right, this is the review for the final. This is the final review sheet that you all have on Blackboard. Covers chapters 13, 14, 15, 16, 17, and 18. I'll go through everything step by step, starting with chapter 13, repeated measures ANOVA. So the question asks, the above data are from a repeated measure study using a sample of the same n equals 6 participants in all three treatment conditions. Use a repeated measures ANOVA with an alpha level of 0.05 to test the significance of the mean difference. Okay, so if you look at this table, we're given some information. We're given G, which is the grand total, N, which is the total N, or big N, of the entire study. We're given the sum of x squared. We're given the means for each group, the t's for each group, which are just the totals for each group, and the sum of squares for each group. So based on all this information given, we will be able to answer this question. So the first thing you want to do is get your DF between groups, or as your textbook labels it, treatments. That is simply k minus 1, which is how many groups minus 1, or treatments. So you can see here, there's 3 treatments. So k minus 1 is 3 minus 1, which equals 2. Next, you get the DF within groups, which is the sum of the DF per group. So each group has 6 participants. So the degrees of freedom for each group would be n minus 1, which is 6 minus 1, plus 6 minus 1, plus 6 minus 1. 15. Next is DF between subjects. Now this is the degrees of freedom of the subjects of just one group. So we're working with equal groups, so it works. And one group has 6 participants, so 6 minus 1 equals 5. Next step is you want DF error. And that's simply you take the DF within groups, which is 15, minus the DF between subjects, which is 5. 15 minus 5 is 10. So now we have all the 4 degrees of freedom that you need for repeated measures ANOVA. Next step is we're going to get the sum of squares. So the first sum of squares I want you to get is the sum of squares total. It's simply the sum of x squared minus g squared divided by n total. Now, all 3 of those values are given to you right here. So you just plug those values into this formula, and it comes out to 152. Next, you want to get the sum of squares within groups, which is just the sum of squares per group added up. So you could see we are given these 3 sum of squares values. When we add those up, we will get the sum of squares within groups, which is 42 plus 28 plus 34 equals 104. Next is the sum of squares between groups, and that equals sum of squares total minus sum of squares within. So sum of squares total is 152, sum of squares within is 104. 152 minus 104 equals 48. All right, the next step is the sum of squares between subjects, which is the sum of each p squared divided by k minus g squared divided by n total. So what we do here is we take each of these p values, square them individually, and divide them by 3, which is k, which is the number of groups individually. So you do 27 squared divided by 3 plus 24 squared divided by 3 plus 21 squared divided by 3 plus 12 squared divided by 3 plus 9 squared divided by 3 plus 15 squared divided by 3. That's the first step. Then you add up all of those values and you subtract it by g squared divided by n total. And if you do that, you will get 84. So that is the sum of squares between subjects. Next, we need SS error, which is SS within groups minus SS between subjects. So that is 104 minus 84, which we just did, and that equals 20. So now we have all the degrees of freedom and all the sum of squares. The next step is MS between groups, which equals the sum of squares between groups divided by the degrees of freedom between groups, which is 48 divided by 2, which equals 24. Then you need to get MS error, which is SS error divided by DF error, which is 20 divided by 10, which equals 2. Now you have both the values you need to get your F obtained. You do MS between groups divided by MS error, which is 24 divided by 2 equals 12. So our F obtained is 12. Now we need to compare that F obtained to the F critical value to see if we have a significant result. The F critical value is using the degrees of freedom between groups on the horizontal plane of the F table, and DF error is used on the vertical. So that would be 2 and 10. So if you go to 2 and 10 on the table at 0.05, you will get a critical value of 4.10. Now, what's the decision on the null? Well, our F obtained is 12, and that's larger than 4.10. So we reject the null hypothesis and have a significant result. Okay, chapter 14. The following results are from an independent measures two-factor study with N equals 3 participants in each treatment condition. Use a two-factor ANOVA with an alpha level of 0.05 to evaluate the main effects and interaction. Calculate the effect sizes for the main effects and interaction. As I mentioned on Blackboard, on your test, I'm not going to ask you to calculate the effect sizes for the main interaction, so we are just going to evaluate the main effects and interaction using their F values, the F obtained, and the F critical to see which factors and if the interaction is significant. So when you're given a table like this, you're given the mean of each group, the sum of squares of each group, and T, which is the total number of scores in each group. If you go across, you'll see T of males equals 54 and T of females equals 90. All that is you're adding up the rows. So that's 9 plus 18 plus 27 equals 54, and 9 plus 36 plus 45 equals 90. Now, the column totals for the T's aren't given to you, but you simply just do 9 plus 9, 18 plus 36, and 27 plus 45, and that will give you the T values for each column. Okay, so the first step is sum of squares between treatments. Sum of squares between treatments, the formula is right here, is the sum of T squared divided by N minus G squared over N. So that is the sum of each T squared divided by N per group. And as you could see here in the work, 9 squared divided by 3, 18 squared divided by 3, 27 squared divided by 3, 9 squared divided by 3, 36 squared divided by 3, and 45 squared divided by 3. You do that step first, and you get all of these numbers. You add these numbers up, and you subtract it by G squared divided by N. So 144 squared divided by 18. When you add up these values and you subtract it by 1152, you will get 360. That is your SS total number, your SS between treatments number. Okay, the next step is SS within treatments. So that's simply the sum of the SS of each treatment. Now, the sum of SS is given to you in each cell. So you just take them and add them up. So 14 plus 26 plus 8 plus 8 plus 14 plus 26 equals 96. The next step is we get SS total. That's simply the sum of x squared minus g squared divided by n. So that's 1608 minus 144 squared divided by 18. And that equals 456. Now, to check your work, SS between plus SS within should equal SS total. And 360 plus 96 does equal 456. So that's a good way to check if you did your work right, and you can move on to the next step. So the next, you have to get SSA, SSB, and SSA by B. All these sum of squares are you're basically slicing your SS between treatments into the different factors and into the interaction. So for SSA, it's the t squared of the row divided by n row minus g squared divided by n. So the way you look at that on the table is rows go left to right, right? Columns go top to bottom. So there are two rows, right? There's a row for male and there's a row for female. Right here, those t values are given to you, right? Because as I explained earlier, it's just the sum of all the t values. So the sum of the t values in this row is 54. The sum of the t values in this row is 90. And n of each row is, well, each row has 9 participants, right? 3 plus 3 plus 3 is 9. So here, you're just going to do 54 squared divided by 9 plus 90 squared divided by 9 minus g squared divided by n, which is 144 squared divided by 18, which will give you 72. The next is SSB, right, where we're looking at factor B, which in this case is the different treatments, and you have to get the t squares of each row divided by n row. Well, how do you do that? You go to these columns, and here they gave it to you. For here, they gave you the totals. Here, you just have to get the totals yourself. So you're simply going to do 9 plus 9, 18. 18 plus 36, and 27 plus 45. Right? Those are the 3 t values of the columns. So now, you take that, and it will be 18 squared divided by 6, right? Because the n, right, there's only 2 cells per column, 3 participants per cell. So the n column will equal 6. So you do 18 squared divided by 6 plus 54 squared divided by 6 plus 72 squared divided by 6. Add them up and subtract that from 144 squared divided by 18, which equals 1152. And then if you subtract the sum of these 3 numbers minus 1152, you will get 252. Now, for the sum of squares of interaction, it's simply the SS between treatments, right? The first sum of squares that we solved for, minus SSA minus SSB. So that's 360 minus 72 minus 252 equals 36. Right? If this came out to 0, it would mean there is no interaction. However, we could say there is an interaction, but now later on we're going to test if that interaction is significant or not. Another thing to also check is SSA by B plus SSB plus SSA should equal SS between, because that is SS between broken down into its 3 different factors. So when you do that, the math is correct and it does equal SS between. So now that you have all of your sum of squares, next step is to get all the degrees of freedom. So degrees of freedom between is simply number of cells minus 1, right? There are 6 cells here. So 6 minus 1 equals 5. DF within is the sum of degrees of freedom in each cell. Well, there are 3 participants per cell. There are 6 cells. So 3 minus 1 equals 2. 2 plus 2 plus 2 plus 2 plus 2 plus 2 equals 12, or you could just do 6 times 2 equals 12. Either way, it's just the degrees of freedom in each cell added together. Next is DFA, number of rows minus 1. Well, if you go up here, you'll see how many rows are there. There's 1 row for male, 1 row for female, So it's 2 minus 1, and that equals 1. DFB is number of columns minus 1, which is there's 3 columns. 3 minus 1 equals 2. And to get degrees of freedom of the interaction, you do degrees of freedom between, which is 5, minus DFA minus DFB. So that is 5 minus 2 minus 1. Now I just put them backwards here, but it doesn't matter. So because you could subtract DFA and B either way. So if you're doing it that way, it would be 5 minus 1 minus 2. But 5 minus 2 minus 1, it gives you the same answer, which is 2. And for DF total, it's simply DF between plus DF within. And that equals 17. Right? 12 plus 5 equals 17. So now we need to get 4 mean squared values. So we have to get the mean squared of A, which is simply SSA divided by DFA. 72 divided by 1 equals 72. For MSB, you just take SSB divided by DFB, which is 252 divided by 2, which equals 126. Then you get MS interaction, which is SSA by B divided by DFA by B, equals 36 divided by 2, which equals 18. And your MS within is SS within divided by DF within, which is 96 divided by 12, which equals 8. All right, so now we want to get the F obtained for each of the factors. So the F obtained of A equals MSA divided by MS within. We are always going to be divided by MS within on a two-factor ANOVA when solving for F obtained. So in this case, MSA is 72, MS within is 8, 72 divided by 8 equals 9. F obtained B. MSB divided by MS within equals 126 divided by 8, which equals 15.75. And FF obtained for interaction is MSA by B divided by MS within, which is 18 divided by 8, which equals 2.25. Okay. The next step is get your F criticals. So to get your F criticals for A, you're going to use the degrees of freedom of A, which is 1, and the degrees of freedom within. So you're always going to use the degrees of freedom of the factor we're looking at and the degrees of freedom within. So if you go to your ANOVA table and you go to 1 and 12, which is DF of A is 1 and DF within is 12, at 0.05, you'll get an F critical value of 4.75. For B, the degrees of freedom is 2 and degrees of freedom within is 12. That does not change. So if you go to 2 and 12 on the chart at 0.05, remember 0.05 is the non-bolded numbers, you will get 3.88, and F critical A by B has the same degrees of freedom as factor B, so 2 and 12 equals 3.88. So now the decisions on the null, now we're just going to compare each critical to each obtained, and if the obtained is larger than the critical, we reject the null. In this case, 9 is greater than 4.75, so decision A, reject the null. 15.75 is greater than 3.88, we reject the null. For the last F critical interaction, the F obtained is 2.25 and the F critical is 3.88. 2.25 is not greater than 3.88, so we fail to reject the null. Okay, these are all the steps that you will have to do on your exam. Okay, moving along. Chapter 15 and 16, correlation and regression. Right, so we're going to use the same question to compute a correlation and then also do a full regression question. So the question asks, for research participants, take a test of manual dexterity. High scores mean better dexterity, and an anxiety test, high scores mean more anxiety. The scores are as follows, right? So you have participant A, you have the dexterity scores, and then you also have the anxiety scores for participant A, B, C, and D, right? All this data is given to you right here. All right, and if you're looking at your practice test, this table will not be filled out. You will have to fill out this table yourself. So the first thing you want to do is fill out the table. So what you do here is you plot all the x values, which is the first variable that's given, which is dexterity, and you plot them. Then you get the mean of that, which will be the mean of x, which is 2, right? By adding 4 plus 2 is 6, plus 1 is 8, divided by 4 is 2. And then you take the deviations of x minus the mean of x. And then on the next column, you square all those deviations, and you will be given the sum square of x. You do the same thing for y. You plot all the y values that were given to you. That's for variable of anxiety. You get the mean of y, which is 5. You do y minus the mean of y. And then you take those values in this column, you square them, you add them up, and this will give you the sum of squares of y. Next, we got to get the sum of the deviation products. How we do that is we take each deviation product, which is the step that we do before we square for the sum of squares, and we cross multiply them together. So we do x minus mx times y minus my for each variable. So -1 times 5, -1 times 3, 0 times -1, and 2 times -7. Gives you these values here. When you add them up, the sum of the deviation products is -22. Okay, so once you have this chart filled out, you could do, you can move along and do regression and correlation. So for correlation, you're simply just going to plug in this data into the formula. R, which is notated as correlation, equals SDP divided by SSX times SSY. So if you do that here, it's -22 divided by the square root of 6 times 84, which equals -0.98. Right? -0.98 represents a very strong negative correlation, meaning when one variable goes up, the other variable goes down. So that's all you're going to be asked for chapter 15. Then we move along for chapter 16. Well, you're going to need the means. So you would have had computed the means to complete the table above. So the mean of x is 2, the mean of y is 5. Now we're going to solve for slope, or b. Right, and that formula is SDP divided by SSX, and that's -22 divided by 6 equals -3.67, or if you're just keeping the values in the calculator, it should come out to -3.6, 10 sixes, and a 7. Again, you could use either value as you go along. It's not going to change the answer too much, and you won't be penalized if you use either method. The next is you want to solve for the intercept, also known as A. To do that, you take the mean of y and you minus, and make sure you put the rest in parentheses, b times the mean of x. Right? So that would be the mean of y is 5 minus, I put the full calculation down from the calculator here. So if you do 5 minus 3.66667 times 2, right? This is a multiplication when there's a parentheses on the inside and outside. You will get a positive 12.33 or 12.34 depending on how you rounded. Now, that's how you get A. So now you have to write the linear prediction rule, equation of the regression line, because we're going to need to use this equation for the next step. So here you simply take the A value. So y hat equals AX plus B, right? So here you can either put -3.67 or the full answer. And then x is where you're going to plug in the original x values or any x value to find out what the predicted y would be using this slope and this intercept, right? So the negative 3.667 is the slope, and the 12.33 is the intercept. So now you have the equation of the line. Okay, so now the next step is you want to fill in the table below to figure SS error using the prediction rule. Show your y hat computations. All right, so all you're doing here is you're plotting the original x's that we plotted above that comes from the data and the original y's. Now, to get the y hats, we are going to plug in these x values into this equation right here. So minus 3.66667 times 1 plus 12.33 equals 8.66, and so on. So again, don't worry too much about the rounding. However you're rounding, you're still going to get the same answer. Even if it's slightly different, it eventually won't change your R, and if it does by a point or a half a point, you'll still get full credit for the answer, just depending how you're rounding. So for this column of y hat, you're plugging in every original x value into this formula up here to get the predictive y's, right? The whole point of this is we want to see, using the original x values, how close are our predicted y's to the actual y's from those x values. So you get 4 y hat values here, and then you are going to go and take the deviations of y minus y hat. Okay? Very similar to what we did above in the first table. So you do y minus y hat, and then you do y minus y hat squared. Okay? This is not times 2. This is just how it came out on Google Docs. This is y minus y hat squared. And if you square all of these numbers, you'll get 1.8, 0.44, 0.98, and 0.12, and you'll get an SS error of 3.34. Okay, so once you have that SS error, you can compute the proportionate reduction in error, which is also known as R squared. You do that by taking the original SSY minus this SS error value divided by SSY. So that's 84 minus 3.34 divided by 84 equals 0.96. Now, to get R from the proportional reduction in error, which is just R squared, you just do the square root of R squared, which is the square root of 0.96, and that will give you 0.98. So this R is to be looked at differently than the original R that we did for the chapter 15 question. This 0.98 tells us that our prediction line is about 98% accurate. All right, you're not going to get negative R's when you're computing this R, because we're really looking at the original Y's versus the predicted Y's, right? So they're not going to move in opposite directions, and when one goes up, one is not going to go down. So this R is really used to see how strong our prediction line is. In this case, it's 0.98, and you can look at it as has 98% accuracy, right? Just for learning, if all the y hats equaled y, then SS error would come out to 0, and R would come out to 1, and it would mean that we have a perfect prediction line. But we don't have a perfect prediction line. Our prediction line is 98% accurate. Okay, moving along. Chapter 17, chi-squared. So, in the United States, 60% of cat owners own only one cat. 28% own 2 cats, 7% own 3 cats, 5% own 4 or more cats. In a survey, students in a statistics course, the following information was found. 50 of the students owning cats had 1 cat, 40 of the students owning cats had 2 cats, 20 of the students owning cats had 3 cats, 15 of the students owning cats had 4 or more cats. So we're asking, is there a significant difference in the number of cats per owner in the student sample versus the nationwide statistic that was given in the beginning. Use the chi-square goodness of fit test using an alpha level of 0.05. Okay, so you're given this table, right? It won't be filled out for you, but you have it. So the given population for one cat, the population percentage is 60%, so I made that a decimal, so that's 0.60. 2 cats is 28, 0.28. 3 cats is 7%, 0.07. 4 more cats is 5%, 0.05. Then we take our observed number, which are given right here. This is the observation of the sample, and we plot them down. So 50, 40, 20, 15, with a total of 125. Now, to get the expected value, you take this total number and multiply it by the decimal version of the given population percentage for each value. So 125 times 0.6, right, or 0.60, it's the same thing, gives you 75. 125 times 0.28, 35. 125 times 0.07, 8.75. And 125 times 0.05 equals 6.25. Right? Now we have our expected numbers. And next step is you want to take the deviations of the observed minus the expected. So 50 minus 75 is negative 25. 40 minus 35 is 5. 20 minus 8.75 is 11.25. And 15 minus 6.25 is 8.75. Now you want to take those values and square them. Negative 25 squared is 625. 5 squared is 25. 1.25 squared is 126.56. And 8.75 squared is 76.56. Okay, so now we take this observed minus expected squared number and divide it by the expected. Right, so 625 divided by 75 is 8.33. 25 divided by 35 is 0.71. 126.56 divided by 8.75 is 14.46. And 76.56 divided by 6.25 is 12.25. When you add all these values up, you should get a chi-square number of 35.75. Now that is your obtained chi-square number. So we can explain that here. Well, you see the critical value for chi-square from the table on page 711 for 4 minus 1 equals degrees of freedom, right? So the first thing we want to do is we want to get the degrees of freedom, right? There's 4 categories here. 4 minus 1 equals 3. That's how you get the degrees of freedom. The critical value, you go to the chi-square table on page 711, you go to degrees of freedom of 3 at 0.05, and you'll see the number 7.81. So that's the critical value. All right, then you'll see CR chi-squared is 32.25. It's just a typo. It should be 35.75. But either way, it won't change the results. Right, you can see here the obtained value is 35.75. And we have the critical, we have the degrees of freedom, we have the obtained value. That was most of the work that we did, which is in this table. And now we just have to make a decision on the null. Well, the obtained value of 35.75 is larger than the critical value of 7.81. So we reject the null hypothesis, and we could say that the cat ownerships of the student sample from the statistics course is significantly different than cat ownership in the population in general. All right, so expect given percentages on your test and a very similar question, and use these tables. Use the practice test without the answer key, where I give all the tables, and also use the practice test as the formula sheet, which shows you how to do the formulas for all these steps to complete this exam. Okay, now on to the last question, which is chapter 18, binomial distribution. So these are 3 formulas that you should know. So mu equals p times n. Standard deviation is the square root of NPQ, and z equals x minus pn divided by the square root of npq, right? This goes back to the same way we used to do z-scores, right? If pn equals mu, it's really just x minus mu once you solve it. And if the square root of npq equals standard deviation, it's just the standard deviation. So the formula eventually just comes out to z equals x minus mu over standard deviation, the same way that we did z-scores on test 1. So now let's go on to do these questions. These are very similar questions that will be on the exam. So to investigate the phenomenon of home team advantage, a researcher recorded the outcomes from 64 college football games on one Saturday in October. Of the 64 games, 42 were won by home teams. Does this result provide enough evidence to conclude that home teams win significantly more than would be expected by chance? Use a two-tailed test with an alpha level of 0.05. Now, if you go back to the lesson for this, you'll see that there are only two critical values that we'll be looking at. If we're looking at a critical value of 0.05, it will be 1.96. And if we're looking at the critical value of 0.01, it will be 2.58. Both are plus minus 1.96, plus minus 2.58. It's binomial distribution, so we're always going to be looking at the two-tailed test critical number. But just know it's either plus minus 2.58 or plus minus 1.96. Okay. So now these are the steps that you should do to fill in and get the answer. So first, n, how many games were there? There was 64, so n equals 64. X, the variable that we're looking to test, were 42 games won by the home team, so x equals 42. Now P is the probability of the event occurring, right? We're looking at wins, home field advantage, see for wins. So the probability of winning by chance would be 0.5, right? And since there's only one option or the other, there P and Q would be the probability of the event not happening, or in this case, the chance of losing is 50% as well. So P equals 0.5 and Q equals 0.5. So now move on to the next step. We want to get mu. Mu is P times 0.64, right? Equals 32, right? It's basically saying that out of 64 games, by chance, you should win half of them, right? So 32 is half of 64. That's conceptually where that number comes from. Now, the standard deviation is the square root of n times p times q. So the square root of 64 times 0.5 times 0.5 equals 4. All right, so now we have x, we have mu, and we have standard deviation. When we have those three values, we know we can compute a z-score. So if you do 42, which is x, minus 32, which is mu, divided by 4, which is the standard deviation, that equals 2.5. Now, the z-critical, it was asking at 0.05, so it would be plus minus 1.96. 2.5 is greater than 1.96, so the decision would be to reject the null hypothesis, right? We do have a significant result. Winning 42 games out of 64 is significantly more than chance. So there seems to be a home field advantage. Okay, last question. On a multiple choice exam with 100 questions, that's n, and 4 possible answers for each question, that should give you an idea of what P and Q will be. You get a score of x equals 32, which is your x value. Is your score significantly better than would be expected by chance? Basically by simply guessing for each question. Use a two-tailed test with an alpha level of 0.05. Okay, so just like the above question, n, 100 questions. X is the score that we're testing. The score is 32. Now P and Q are going to be different here, right? You still can only have, right? It's still a binomial distribution because you either can get it correct or incorrect. But on the multiple choice test, there's 4 possible answers. So the probability of getting an answer correctly by guessing is 1 out of 4, hence YP equals 0.25. Now the probability of getting an answer incorrect is 3 out of 4, hence YQ is 0.75, right? 1 divided by 4 is 0.25, 3 divided by 4 is 0.75. Okay. Next step, we do mu, that's P, which is 0.25 times 100, equals 25, right? So to think about it, that's getting 25 out of 100, right? That's the proportion of 1 and 4. It's the same thing if you get 25 out of 100. So that's the hypothetically saying, by chance, you should get 25 correct out of 100 if you just guess. The next is standard deviation, the square root of 0.25 times 0.75, which is P times Q times 100 equals 4.33. Plug in the x and the mu, 32 minus 25 divided by 4.33 is 1.62. And the z critical here, again, there's only two possible z criticals. I'll say it again. It's plus minus 1.96 for 0.05 and plus minus 2.58 for 0.01. So we look at our z obtained. It's 1.62. That's smaller than 1.96. So we fail to reject. And, conceptually, we could just say that our score is not significantly better than what would be expected by chance. Is it higher? Yes. Chance would be 25. We scored 32, but 32 is still not a high enough number to say that we did significantly more than chance. Good luck on your test, everybody. If you have any questions, email me. Best of luck.